This is a video for AQA Mechanics, Center of Mass and Moment, section 1.1, which introduces the idea of the moment of a force. So far we've considered objects as being particles, and now we're going to look at the idea of forces acting on a rigid body. Now, by a rigid body we might think of a plank of wood, maybe a ladder, or maybe a metal plate. Basically, we're assuming that it remains rigid and does not deform when the forces act upon it. So if we think about the diagram that we've got here, we can see that there are two weights which are acting down in this way, and each of those will tend to turn the seesaw about the axis at this point here. There will also be a reaction force where it's supported, so there will be a normal reaction at this point here. So those two weights are going to produce turning forces about this axis here, which we might say is x. And that turning force is referred to as the moment of a force. We define the moment of a force m as being the force multiplied by the perpendicular distance of the force from the axis. So in this diagram here, if O is the axis, then the perpendicular distance d is this distance here on the diagram. So force multiplied by perpendicular distance. Now, because force is measured in newtons and distance in meters, then the moments have units of Newton meters, or Nm. Well, moments can cause the object to turn either clockwise or anti-clockwise about the axis, and by convention we take anti-clockwise as being the positive direction. So here you can see this particular force is going to be turning in a direction about this axis here, which is anti-clockwise, and therefore we would say that that has a positive moment. Let's now consider an example where we've got two forces. A 50 Newton force, which is acting at right angles to the line from x at a distance of 0.3 meters. Therefore, because we've got a perpendicular distance here, we can say that the moment of that force is 50 multiplied by 0.3. So that gives us 15 Newton meters. And because it's an anti-clockwise direction about x, we would say that it's positive 15 Newton meters. For the 10 Newton force, however, we can see that the distance that we're given is 0.7 meters. However, it's not a perpendicular distance. So what we need to do is to use a little bit of trigonometry here to work out that the perpendicular distance is given by this distance here, d, and then we can see that by vertically opposite angles there, this one here must be 60 degrees, and so therefore d is equal to 0.7 multiplied by sine 60. And so that the moment of that force will be the force which is 10 and then multiplied by the perpendicular distance 0.7 sine 60 degrees. And now, because this is an clockwise direction rather than an anti-clockwise direction, we would say that that is a negative moment. And that turns out to be negative 6.06 Newton meters. So we therefore have a total moment being equal to the sum of those is 15 and then minus 6.06, so a total moment of 8.94 Newton meters. So here we've got the full calculation. You can see that we've got the perpendicular force there, 50 newtons at a distance of 0.3, and here we had to calculate the perpendicular distance for the 10 Newton force by using 0.7 sine 60. You could have done this in one calculation, so we could have said that the total moment was equal to the 50 multiplied by 0.3 and then minus the 10 multiplied by 0.7 sine 60 degrees as being the total moment to give us the answer 8.94 Newton meters. Well, as an alternative method, instead of working out the perpendicular distance as we've just done for the 10 Newton force, then we can take the component of the force which is acting in a perpendicular direction. So we need to calculate this component here. Of course, if we've got a 60 degrees, then here this would be 30 degrees, which is perpendicular. Now that component is acting at right angles to the direction towards x. The other component would be acting along the line here. So because therefore the distance, the perpendicular distance of that component is 0, it actually goes through x, then that provides no turning moment. So it is only the perpendicular component that we need to take. So if that perpendicular component, we've then got 10 cosine of 30 degrees, and we're multiplying that by the perpendicular distance, which is 0.7 meters. And because it's a clockwise moment, then that would be negative of that value, which again of course gives us a value of negative 6.06 Newton meters. The 50 Newton force is again at right angle, so therefore it has a 15 Newton meter turning moment, and again anti-clockwise for that one, so that would be a positive moment. So let's look at this method then. The perpendicular force as before, just a different way of thinking about the force which is at an angle to the line of action. This time we've taken the component which is at right angles to that line of action. In other words, the component is 10 cosine 30 degrees. Multiplying that by the perpendicular distance of 0.7 gives us a moment about x of negative 6.06, the negative being because it's a clockwise moment. In summary then, we have the idea that the moment of force is the magnitude of the force multiplied by the perpendicular distance. So force multiplied by perpendicular distance d. The moment of the force is by convention positive if it is in the anti-clockwise direction and negative if it is clockwise. Units of force, Newton meters, and then two ways of dealing with a force which is acting at an angle. One is to work out the force multiplied by the perpendicular distance. So here we've got our perpendicular distance d. The alternative to that is to calculate the distance multiplied by the component of the force which is perpendicular to the line of action. So instead of that, we could take this force here, which is the component of F at right angles. That then concludes this video on moments, and in the next one we'll be looking at centers of mass.